Okay, so we'll crack on with these generating functions. And we stated initially that the generating function would guarantee the transformation to be canonical if it contained one of the old and one of the new variables. So we've considered two of them so far, meaning that there are two left. And the third one is the following. And let me give you the fourth one right away. Now, out of the four possible generating functions, we see that the fourth one is the most complicated of them. It's the largest, at least. So if you can find the transformation equations for this one, well, then you can master all four of them. So I wanted to give you that challenge, namely derive the transformation equations that are generated from this f. So we'll take 5 to 10 minutes for that. Yeah. Anyone cares to give it a try? Okay. Mm-hmm.
Jeg har kanskje ikke skrevet dem som Q. Jeg liker dem i hvert fall.
Mm.
I lille QI pluss DF4D lille P skal være litt null.
QE, så er det pluss.
Ja.
Okay, plus DF4 DPI, like this. Okay, and then?
Minus store QI pluss DD lille p ser det ut som er lik null. Nå ser mine p-er ut veldig som små og store p-er, så det må vi sjekke. Men DP lille p og så lik null.
Like this?
Ja.
All right, and then the third one?
Den siste sier bare at lille p er lik store p. Det er litt rart, men det er forstått.
Okay. So these are the equations you obtain. So what about the Hamiltonian H? Did you find some condition for that? Because there's been a pattern for the three preceding. Like this. All right. So this looks good. I'm a bit puzzled about this one, but we'll check. Okay, so this is a suggestion. So let's just plug this into our equation and see what happens. All right, so starting off with the left-hand side, we have this. So we should get this. Okay, we should be able to do a couple of cancellations here. Like these terms. They just cancel each other. And moreover, we have cancellation here. So that leaves us with this. Oh, sorry, I canceled the wrong term here. I should cancel this one. This one should remain. So let me just exchange here. So at this point, it's just a matter of pairing the terms with equal time derivatives. What we have corresponds here and here, which gives us qi plus the partial derivative of f4 with respect to pi is 0. So this one's good. And then we have a term here. So it looks like this should be a large P.
Yeah.
So let me just turn it into large P. So that's okay. And then we just have the remaining terms here, which follows the generic pattern we've seen so far. Namely that K is equal to H plus the partial time derivative of f4. And this is exactly what you have here. So all in all, I think you were right. The only thing I'm a bit puzzled about is this one. How did you get this one?
I probably didn't, just messy.
Mm.
Maybe I cancelled the wrong term.
Okay.
Or something.
Yeah. But these three equations are correct. So now that you have done the F4, the fourth case, you can do the 3 first without any problem. So let me just, for the sake of completeness, also write down for the third case. The following. Okay, so it's about time to consider a couple of examples to see what this can be used for and why it can be convenient to make such canonical transformations. We'll start off with an example which is meant to illustrate that these canonical transformations actually don't have to be very exotic. They correspond to some cases that we already are very familiar with. Consider, for instance, the following case. The generating function is the sum over small q's multiplied with large p's. Now this is consistent with the definition of f2 that it should depend on small q and large p. And we now know that for this type of generating function, depending on small q and large p, the transformation equations look like this. This is the first one. Which just tells me that pi is small pi is equal to large pi. The second equation is this. Which tells me that the old and the new spatial coordinate is the same. And finally, since there is no explicit time dependence in F2, the Hamiltonians h and k are the same. We get k just by inserting the new coordinates into h. So in other words, this generating function generates the identity transformation. And I'm not saying that for F2 in general, but this particular function, which belongs to the class F2, does generate the identity transformation. So that's one particular example. We can consider a slightly different form of F2. So instead of having qi multiplied with large p, consider now a function, an arbitrary function, depending on all these generalized coordinates multiplied with p. Now this generating function still belongs to the second class because it's a function of the small q's and large p's. So using now the general transformation equations, for instance this one, we see that this function generates a transformation so that the new coordinates are a function of the old coordinates and not the old momentum. So in other words, this is exactly a point transformation. This corresponds to, for instance, going from Cartesian to polar coordinates. So put differently, a point transformation is a special case of a canonical transformation. So this initial example is meant to illustrate that the generating function belonging to the class F2 contains some important limiting cases. It contains the identity transformation, and it also contains the point transformation. So we'll consider a new example now, which is meant to illustrate more sort of the convenience in understanding the physics of the situation by means of the canonical transformations. So let's say we have some system which is described by the following Hamiltonian. So we're just considering one particle, for instance, for simplicity. So it depends on position momentum like this. Now, what kind of system is this? What kind of physics does this Hamiltonian describe? Well, it's not so easy to say. This probably doesn't look like anything you've seen before. So judging from this form, we can't immediately say what we expect for the behavior of the positional momentum. However, we can try to make a canonical transformation to a new set of coordinates so that the Hamiltonian in this new set of coordinates takes on a well-known form which we are familiar with. So, let's try to introduce a new set of coordinates which looks like this. The Hamiltonian now takes this form. So let me again pose the question. What kind of physics does our Hamiltonian describe? This is something you have seen 100 times before.
Maybe a harmonic oscillator.
Okay, why?
Well, we have the position squared and momentum squared, so that works fine with.
Absolutely. So we're more accustomed to seeing it in the form something like this, where this is the kinetic energy and this is the potential energy. But this can be written in the following form just by rescaling P and X. So we just absorb 2m into the momenta and absorb this coefficient into X. So this is essentially exactly the same thing as this. So just as you say, our original mysterious Hamiltonian was in fact a harmonic oscillator in disguise. So we eliminated the disguise of the Hamiltonian just by introducing this set of transformations which brought H to our well-known form. And now we know exactly how Q and P should behave. Q should be some sinusoidal or cosine function, harmonically oscillating. And similarly, the momentum also has a well-known solution. Yep.
But how do we know which transformation to make? Which is convenient?
So there's no a priori reason for how you should know this. You basically would have to inspect this and see if you can bring it to some well-known form. So this is, you can think of this as an educated guess, actually. You wouldn't know beforehand how you need to transform it. You would have to look and see, can we bring this to some new well-known form? However, there's a very important caveat here, actually a pitfall. Can we be sure that this is in fact, that this transformation gives us the physics of a harmonic oscillator just because H looks like this?
true if the transformation is canonical.
Yep.
But I can't explain why.
Okay, so it's intuition. Well, you're absolutely right. We can only expect the physics of a harmonic oscillator if the Hamiltonian has this form, if Q and P are canonical coordinates. And the reason for this is that we know beforehand that if the Hamiltonian has this form and these P and X satisfy Hamilton's equations, we know the physics. This describes a harmonic oscillator. But it relies on the fact that these coordinates are canonical, that this is a canonical transformation. I can, in principle, make any transformation. I can make some complicated, I can introduce P as the sine of Q squared plus exponents of P or something like that. I can do anything I want, but that doesn't mean it's a canonical transformation. So in fact, we should check that this is in fact a canonical transformation. And if it is, then we can be sure that this describes the physics of a harmonic oscillator. So if the transformation star here is not canonical, then the new coordinates P and Q do not satisfy Hamilton's equations, in which case it satisfies something else, which we would have to solve to find out how Q and P behave. But if they satisfy Hamilton's equations, well then we know from this textbook example what we should expect. So the task is now to check if these are indeed canonical transformations. If they are, they should be possible to obtain from one of the 4 generating functions. So let's see. Let's try with the following. The fact is that this transformation is generated by the 3rd generating function. And in fact, it has to have this specific form. We know the general transformations equations for the 3rd class of generating functions. Namely, these 2 equations here, F3. And there's no explicit time dependence here, so the old and the new Hamiltonian should be the same. So let's check if these equations, these transformation equations, are now consistent with these. Okay, so large P minus partial derivative of Q here, so it should be minus P, or Q squared. And the second one is Q equals minus df3 over dp which looks like this. So there's a problem here, which I see now. Well, this equation is okay. This equation is consistent with this one. But here, if I now insert this q into here, I get large P is minus P q squared. So there's some sign error here. Do you see it? So let me try something. Let's say I put a minus sign here instead. In that case, I get plus, and I get plus here. So I think I missed a sign here. But the result is the same. If I define q is plus or minus 1 with q, it doesn't matter. Because it's only q squared and q to the power of 4 that enters. But we see here that the sign is very important to make the transformation canonical. So if I now revise this slightly, I introduce these transformations. The result is the same. I only have plus here instead of minus. And I introduce f3 as follows.
Well, when you found the large P, you should have minus the ft large Q, and the f large Q is minus P over Q squared.
Oh, so it was correct from the beginning, perhaps.
So then large P should be P over Q squared.
Okay, so let's see. We start with this. So let me take back the minus sign here. We have this, and then minus, and then we get an extra minus, so it's plus. Right, okay. And then we should have,
Then you can keep the minus.
here I keep the minus, insert it here, and get plus. Yeah, okay. So sorry about the confusion. It should indeed be minus here. So then the point is that the sign still matters. If we have chosen plus, the transformation wouldn't have been canonical. And that's an important point because there are then many ways, or at least two ways, we can obtain this Hamiltonian, which looks like a harmonic oscillator, but only one particular choice of the sign here will guarantee that it's canonical, so that it describes the physics correctly. So F3 looking like this guarantees its canonical nature. Okay, I think we'll stop there. Perhaps I'll see you tomorrow, and if not, I wish you a nice Easter holiday.